ever stopped to wonder why water is, wet? Or why a diamond is so unbelievably hard? Well, the secret isn't just what they're made of. It's all about how they're built. We're about to take a look at the hidden geometry that basically rules our entire world. So let's kick things off with a simple little mystery. We're going to look at two molecules that you encounter every single day. Water, of course, and carbon dioxide, the gas we all breathe out. Right away, you can see something's different, right? A water molecule is kind of bent into a V shape, but a carbon dioxide molecule, it's a perfectly straight line. Now they both have just 3 atoms, but their shapes are completely different. Kind of weird. And that brings us to the big question. Why does this tiny little difference in shape have such huge, enormous consequences for everything? Well, the answer comes down to a single, really elegant rule. This rule is the absolute key to unlocking the whole mystery of why molecules have the shapes they do. And it's all about electrons and the fact that they really like their personal space. Okay, so the official name is VSEPR theory, which I know is a mouthful. But the actual idea behind it is super simple. All the electron groups hanging around a central atom have a negative charge, right? So they push each other away, they repel, and they're always going to arrange themselves in 3D space to get as far apart from each other as possible. That's literally it. This constant pushing is what dictates the final shape of the molecule. And the cool part is, we can use this like a simple 3-step tool. First, you just find the atom smack in the middle. Second, you count up all the electron groups surrounding it. And third, you just figure out the geometry that gives them all the most breathing room. Simple as that. So let's put this rule to the test. Let's see how this one idea helps us build a whole library of predictable, fundamental shapes that you see all over chemistry. What's so amazing is just how logical this all is. Take a look at the table. If a central atom has 2 electron groups, like our old friend carbon dioxide, they are going to push to opposite sides a 180-degree angle and make it a straight line or linear. Got 3 groups? They'll form a flat triangle with 120 degrees between them. And with 4, you get a 3D shape called a tetrahedron with perfect 109.5-degree angles. These are our ideal basic blueprints. But here's where the story gets a plot twist. So far, we've only talked about electrons that are busy bonding atoms together. But what about the electrons that are just kind of hanging out on that central atom, not actually part of a bond? Well, these are called lone pairs. And believe me, they are total game changers. Let's do a quick comparison. On the left, you've got methane, CH4. It's got 4 bonding pairs, 0 lone pairs. So it forms that perfect tetrahedral shape we just saw. But now look at ammonia, NH3. The nitrogen in the middle also has 4 electron groups around it, but one of them is a lone pair. And this lone pair acts like a bully. It's extra repulsive, takes up more space, and it literally shoves the other 3 hydrogen atoms down, squashing the whole shape into a pyramid. This table just lays out the pattern perfectly. If you start with 4 total electron groups, 0 lone pairs gives you a perfect tetrahedral. 1 lone pair squashes it into a trigonal pyramid. And 2 lone pairs? That brings us right back to our original mystery, water. The oxygen in H2O has 2 bonding pairs and 2 of those powerful lone pairs, which push the hydrogens even closer together. And that signature bent V shape is what makes water, well, water. It creates a positive and a negative side, which is why it's so good at dissolving almost anything. Okay, so we've cracked the code for single molecules. We get it. Now let's zoom out a bit and see how these individual little shapes pack together to build the solid materials we actually see and touch every single day. So the way these individual molecules pack together totally determines the properties of the solids around us. Let's look at the 4 types. First, You have ionic solids, like table salts. They are these rigid crystal grades, which is why they have super high melting points. Then there are molecular solids, like ice. Here, all those individual bent water molecules are held by pretty weak forces, which is exactly why ice melts so easily. Then we have metallic solids, like copper, which are basically a sea of shared electrons, perfect for conducting electricity. And finally, the real powerhouse of the group, covalent network solids. And this brings us to diamond. The whole secret is its structure. It's just one giant 3D network of carbon atoms where every single one is at the center of a perfect tetrahedron, just like we saw with methane. It's this incredibly strong interlocking grid that gives diamond its legendary hardness. The tiny microscopic shape directly creates the huge microscopic property. So cool. Okay, this is all fascinating stuff, but let's make it practical. Let's see how we can actually use this knowledge to nail some real questions you might find on an exam. All right, here's one from a past JAMB paper. We literally just talked about ammonia. You've got that central nitrogen with 3 bonds to hydrogen and that one bossy lone pair. So what shape does that create? Take a second to think about it. And the answer is C, trigonal pyramidal. That powerful lone pair pushes the 3 hydrogen atoms down, creating the base of a pyramid. Even though it starts from a tetrahedral arrangement of 4 electron groups, that lone pair totally distorts it. Let's try another one, this time from WAEC. Which of these molecules has a linear shape? Now remember, for a shape to be linear, perfectly straight, the electron groups on that central atom need to be 180 degrees apart. So which one fits the bill? The answer is D, CO2. The carbon atom in the middle is bonded to 2 oxygen atoms. Those 2 groups act as our electron pairs, and to get as far apart as possible, they just push to opposite sides, forming that perfectly straight linear molecule. So what are the big takeaways here? First, everything is governed by one simple rule. Electron pairs push each other away. Second, those unshared lone pairs are the bullies. They're extra repulsive and they distort the final shape. And third, and this is the really amazing part, this tiny microscopic geometry is what creates the huge, large-scale properties of the materials that make up our world. So, the next time you see ice melting in a glass or you admire a diamond, you'll know the secret. You're not just looking at a substance anymore, you're seeing the result of countless tiny geometric shapes, all just following one simple rule. Now that you can see this hidden architecture of the world, what are you going to look at differently? Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy-to-understand lessons. And hey, want to practice more questions and get step-by-step solutions? Visit www.examkp.com right now and keep learning smarter.